Welcome to solverfy.
In order to answer this question, we need to recognize the relationship between the strength, the intermolecular force strength, and the boiling point of a substance. It turns out that we get the highest boiling point when we have the strongest intermolecular forces. Recognizing that the highest boiling point comes from the strongest intermolecular forces, then all we have to do to determine which one has the highest boiling point is to identify which one has the strongest intermolecular forces. The first set of two that is provided is propane and butane. Carbon and hydrogen have very similar electronegativity values, so we typically think of the arrangement of a hydrocarbon, these both being hydrocarbons, as being nonpolar, and the intermolecular forces that predominate are London dispersion forces. So if both of these have the weaker London dispersion forces, then which one will have stronger London dispersion forces? Well, as you recall, the London dispersion forces increase in strength as the molar mass of the substance increases. So butane is going to have a larger molar mass, therefore stronger dispersion forces and a higher boiling point. The next set of two molecules is diethyl ether and this butanol. So these are mostly hydrocarbons also. This oxygen can allow for dipole-dipole interactions to occur, and this OH can allow for hydrogen bonding to occur. Typically, when we compare the strength of hydrogen bonding and dipole-dipole, hydrogen bonding is usually much stronger. So because these molecules are about the same size, we won't consider comparative dispersion forces. We will compare the strength of the dipole-dipole intermolecular force with the strength of hydrogen bonding, where hydrogen bonding is greater. Because hydrogen bonding results in a greater or stronger intermolecular force, then this molecule will have a higher boiling point. The next two are SO2 and SO3. It might be helpful to draw the Lewis structures, so I went ahead and I drew the Lewis structures for both of these. We see that this molecule is bent. There's a slight difference in electronegativity between sulfur and oxygen. So we would say that this end is partially negative, while this end is partially positive. Sulfur trioxide is trigonal planar, so any electronegativity difference between the sulfur and the oxygen is canceled due to the trigonal planar geometry of sulfur trioxide. So we'd be inclined to say that this one is polar and this one is nonpolar, suggesting SO3, being nonpolar, would have the predominant weaker dispersion forces. It turns out, although not very obvious, that this dipole is fairly weak due to the small difference in electronegativity between sulfur and oxygen. So when comparing these two, we really shouldn't compare the dipole force here and the nonpolar dispersion forces here. We really should be comparing the dispersion forces of the two. The dispersion forces, similar to what we determined up here, increase with molar mass. So because sulfur trioxide has a greater molar mass, it will have greater dispersion forces and a higher boiling point. And this is the case if you were to look up these two molecules. Sulfur trioxide has the higher boiling point, suggesting stronger intermolecular forces. The next two are Cl2CO and H2CO. Both of these have very similar Lewis structures, which I'll show you here in a minute. The only difference is we have the more electronegative Cl2 the more electronegative chlorine in Cl2CO and the less electronegative hydrogen in H2CO. Because the chlorine is more electronegative than hydrogen when bonded to carbon, then it is going to pull more electron density towards it, resulting in a greater dipole force, where we would have a greater partial negative down here. In addition, the chlorines have greater molar mass than hydrogen does. So both of these together suggest greater dipole-dipole force and greater London dispersion forces. Because this has both of those, then it's going to have greater total intermolecular forces and hence a higher boiling point.